1 and 4. Okay, so today we'll start thoroughly. All the basic definitions, so let me write down again what a Lie group is. So G is a Lie group, so one condition was it's an n-dimensional manifold. Particular, so I include as usual that it has countably many components. So second countable if you want to. And then it's also a group. So I have a multiplication, and I have an inverse. And I require that M and I are smooth. So these are my two conditions. First, it's a manifold. It has a group multiplication, and this multiplication is smooth. I don't care that much about what smoothness. Remember last time we said C1 implies infinity, implies analytic. Usually when we actually look at examples or have a discussion, it's usually clear from context that it's C infinity, so I'm not going to care. Particularly, I won't prove the result that C1 implies C infinity. This will not be important for us. Okay, so that's a Lie group, and then the other concept that was important also last time was a Lie algebra. So we call it V, a vector space with a bracket on it. So the bracket is a bilinear form that goes from V cos V into V. So it's linear in each component, as usual, right? So maybe this is, say, a vector space. V is a vector space over the reals or the complex numbers. So they're real Lie algebras and they're complex Lie algebras. And it satisfies our Jacobi identity. And so cyclic commute. I always have to do it like this. So x, y, z, x, y, z, and then x, y, z. This is 0 for all x, y, z in the vector space V. Okay, so that's a Lie algebra. Simplest examples of a Lie group in Lie algebra. So I think I mentioned this already last time, GL and R. So invertible n by n matrices is a Lie group. But it's open inside a vector space, so it's open in n by n matrices. So it's clearly a manifold. It's an open set in the vector space, clearly a manifold. And if I multiply it to two matrices, that's just the polynomial in the components of the matrices. So that's smooth. And of course, A inverse, if you think of Cramer's rule, times a matrix of minus, right? That's and T is polynomial, and this becomes algebraic. So these operations are clearly smooth. So general linear group is clearly a Lie group. And then I can also do the complex numbers. So GL and C is, of course, similarly a Lie group. And yes?
In Lie algebra, for a bracket has to be symmetric.
I forgot that. You're right. Thank you very much. Very important. Absolutely. Let's be symmetric. Thank you. And the simplest example of a Lie algebra is, say, R3 with the cross product. Right? So cross product on R3 has all these properties. It's Q-symmetric. It satisfies Jacobi. So that's a Lie algebra. Okay. Then the relationship between the two is obtained by left invariant vector fields. So by the way, my Lie groups are finite dimensional. There's also a concept of an infinite dimensional Lie group. For example, the diffeomorphism group of a manifold is certainly a group in some sense. If you want to make that into a Lie group, then you have to, then things become rather technical and difficult. You have to make it into some kind of manifold. So this subject is quite different from, say, finite dimensional Lie groups. I will also see things of finite dimension. For Lie algebra, I guess also here V is an n-dimensional vector space. So everything I do will be finite dimensional. Okay. So when I have a Lie group G, I have left translations and right translations. These are clear diffeomorphisms. The inverse, what is LG inverse? That's just multiplying by G inverse. Right multiplying. It is right multiplication by G inverse. Right? Is that right? A goes to GA, so if I take GA inverse, this A inverse, G inverse. What am I doing wrong? No. It's LG inverse, right? Of course. Right, G inverse times GA is equal to A. So LG inverse is LG inverse. So of course, these are both differentiable. So it's a diffeomorphism, right? So I have left and right translations which are diffeomorphism. Then I define what is called a left invariant vector field. So L is a vector field on this manifold G. It's called left invariant. If it's invariant on left translations. So that would be, say, the shorthand form. If you want to crank it out, this must be true at every point. Right? So the derivative of left translation at some point h applied to x at the point h must be equal to the image point x at the point g times h, which is whether it's defined. So this must be true for all g and h.
The other way around, isn't it?
One.
H times g.
This is a derivative at the point h, so it takes the tangent space at the point h into the tangent space at the point gh.
But isn't it a left translation?
What?
No.
Okay. So that's the equation that one has to be satisfied. And now we have the following simple lemma or proposition. So I'm going to give this set a name. So let if G is the set of all left invariant vector fields, on G, then I get a linear map from this vector space G into the tangent space of G at the identity, which sends my vector field X into the value at the identity. Okay. So I put the point as a foot point of the vector field. Okay. So I claim this is an isomorphism. Of vector spaces. And this G is then going to be called the Lie algebra. So, but let's first convince ourselves that This is an isomorphism, and I can then describe particular the vector field equivalently as its value at the identity. Particularly it's finite dimensional. Sort of all left invariant vectors finite dimensional. The result is almost obvious. Well, certainly L is 1-to-1, right, clearly. Right, what is if X, so what is X at a point G is derivative of LG at the identity applied to X at the identity, right? So set H equal to identity. So this must be particularly be satisfied. That's a special case of definition. So if I know X identity, I know the F at every point, if it's left invariant. Right? So of course that means that if this is 0, then X is 0. So it's 1-to-1. Now I want to show it's onto. I think it's almost obvious, right? Because certainly that's how you define it, right? Given a vector at the identity. So given, let's call it V. Define a vector field by saying X at G is derivative of LG applied to V. That defines a vector at every point in the Lie group. That certainly has to be satisfied if it's left invariant. That's one of the properties. And now I have to verify two things. First, that this equation is true for all G and H. Right? By definition, it's true for H equal to identity, so now I want to check it for all G. So that's the first part. And that's going to be easy. What's a little bit trickier is that you have to show it's smooth. So A is X left invariant, and for B is X is smooth as a vector field. Right? I want this to be a sort of smooth vector fields G. So part A is easy. So what did we say? I have to verify that if I differentiate this at the point H, applied to X at H, this should be equal to X at GH. Right, that's what I have to verify. So, well, what is X at H? I have to find X this way. So I use a definition. So the left-hand side is derivative LG at the point H applied to derivative of LH at the identity applied to V. So I'm plugging in the value according to the definition. And now I can use a chain rule. Right, so this is a composition of two diffeomorphisms. So chain rule says that this is true. And now the composition of two left translation is just a left translation by GH. Right, if I first multiply by H on the left, and then by G on the left, the same thing as multiplying by the product on the left. So of course this is then by definition, well, so if I look at this definition here, that's precisely the vector at the point G times H. Okay, that's it. So left invariance is just plugging in and using this fact about left translations. Smoothness is a little bit trickier. In fact, many books just leave it out, right? They just say, "Now I'm done," and they don't prove that X is smooth. That's cheating. So how do I want to do that? Maybe I can. I do it in local coordinates, right? So we can prove smoothness in local coordinates. And for this, I want to regard vector field as a derivation. Right? One possible way to study vector field is as a derivation. So X is a vector field. I can also regard it as a map from C infinity M to C infinity M, right, which takes a function into a derivative of f at the point P applied to X at the point P. Right, that's another way of looking at the vector field. It's a derivation. It satisfies the derivation rule. And one way to show that a vector field is smooth by choosing local coordinates. Say yi on G, on M in general. And then showing that the vector field X applied to the coordinates yi are smooth. Right, so X is smooth if and only if this is true. In fact, then the vector field X I can write as X is summation X applied to yi ddyi. So that's the usual way of working with vector fields as a derivation. So I want to show that these things are smooth here. So I do this for my Lie group. And now I have to do this just the right way. So what is so I have my left and right vector field, right? X at the point G was d LGE applied to the vector V. That's my definition. I want to show it smooth. So I take, I want to apply XG applied to the coordinate functions yi. Right, so that's the derivative of LG at the density applied to V. That's a vector. And I want to regard as a derivation, so I apply it to my function, to my coordinate function yi. So your yi, they go from an open neighborhood into the reals, right? My coordinates. And now to apply the chain rule for derivations. Right? So do you remember how that goes? This is what? So V is a derivation, right? This is diffeomorphism. I apply diffeomorphism to a derivation. I did a new derivation. And what's the value? There isn't much choice, right? It must be, I have to use it V as a derivation. So I have to apply V to a certain function. And what's the natural function? Composition of yi with LG. Right? So that's how it works as a derivation. So V applied to that. So let's write V as summation bi ddyi in local coordinates. And this would be summation bi. Let's say b, let's do a different index, bk. The name of the index doesn't matter. bk ddyk of yi composed with lg times ddyk. Well, what is that? If I apply a function to the coordinate vector field to function, I get the partial derivative of the function. Right, so this becomes a derivative of yi composed with lg in the direction of yk. ddyk. Now I'm done, because I can say there, this is smooth, since the left translations are smooth. Because this now just a set of partial derivatives of left translations in that coordinate. Como? Onde?
Na expressão de cima. Não tem que só colocar esse último vetor no final.
Ah. Certo. Melhor? Obrigado. it's a function after all, right? The function is supposed to be smooth. Thank you. Okay, that's it. So it's not very hard, but it is something one has to verify. Okay, so now I have these left invariant vector fields, and I claim this makes G is a Lie algebra. Since the Lie brackets, so since if x and y are left invariant, this I claim implies that the Lie bracket is left invariant. Right, this is just due to the fact of one of these properties of Lie brackets that LG star of the Lie bracket is a Lie bracket of the LG star for any diffeomorphism. Right? And that's xy. Right, so this equation here is a usual kind of equation for Lie brackets. Right? So I got a Lie algebra. Associated to every Lie group, I have a natural Lie algebra. So when G is a Lie group, I say that G is a Lie algebra of G. And I do sometimes, I'm going to use this identification that I can look at the Lie algebra in two different ways. Right? I can look at it as vector fields which are left invariant, or I can look at it at the vector space which is the tangent space at the identity. These are two different ways I can use to view it. Okay. Maybe, again, a quick example. In fact, the most important example. In the end, the only example where I have to compute the Lie bracket. Right, so in general, this may be something that's not so easy to compute. I give you a Lie group. I would have to write down what the left invariant vector field looks like, and I have to take Lie brackets. That may be a little bit nasty in general, but it essentially all reduces to the following example, which we discussed earlier. So let me do it in the following generality. Say V is a vector space over R or C. We are a complex vector space. Then I have the endomorphism of the vector space. So just all linear maps. And I have what I want to call the GLLV sitting inside there, which are the invertible linear maps. So invertible endomorphisms. Of course, if I think of this as a basis, this would just say that the determinant is non-zero. So certainly this is an open set in here in general. Right, so GLV is open in the endomorphism vector space. Right? This is a vector space. That's an open set in this vector space. So it's certainly a manifold. As I discussed earlier, it's a Lie group. I could choose a basis, and it becomes a polynomial and so on. But now I have to compute the Lie bracket. So again, for this, it is easier to identify this as matrices to do it in a basis. So I want to call this say K, where K can be R or C. That's my notation for n by n matrices over the reals or complex numbers. I'm going to use that from now on. And then I have this invertible matrix inside there. So now I want to study what is a Lie algebra of the general linear group. So that's my notation. And I want to claim that if I have, say, x and y inside the Lie algebra, then the Lie bracket is just a commutator. The sense of linear maps, right? In this composition of linear maps. So it's just a commutator. Again, the simplest kind of Lie algebra, if you want to, after the one we discussed earlier, just commutators of matrices are a Lie algebra. Okay, so I want to claim this. I want to prove this claim here. Okay. Lots of books make this into a complicated proof, but it's actually quite easy because of linearity. There's lots of linearity going on. So let's view this as X as a vector field on the n by n matrices after choosing a basis. So then I'm going to denote this as A goes to X at the point A. If A is a point in GL V, or how should I denote this? Inside the invertible n by n matrices. I don't have a good name for that. So at each point in the invertible matrix, I have a vector at that point, because this is a vector space, right? So I'm going to use the structure of the vector space. And I claim, what's the value? The value is very simple to describe. I claim that X at the point A, X sub A, is simply A times X. So now with the understanding, this is a vector space. The tangent space identifies the vector space. Right? This, of course, is then just another matrix, which lies in here, and therefore also in the tangent space at A of the vector space. Okay, so those identifications I make. And why is this the case? Well, what's left translation by A? So that takes B to AB. That's linear in B. Right? So therefore, the derivative is a map itself at any point. And of course, left and right vector fields are defined as apply left translation and then evaluate it, right? So to have less than is just multiplication by A on the left. So this is true. Now I want to take the commutator. And I'm going to do this in coordinates, right? If I want to compute Lie brackets, it's usually best to do this in coordinates. So here the Lie group is an open subset in the Lie algebra.
Yeah, but this is not a vector field itself.
Pardon?
But this is not a vector field itself, I think. GLV.
This here?
No, GLV. The Lie group is not a Lie algebra, right?
No, but so GLV sits inside the endomorphism of V, right? And the Lie algebra GLV is actually equal to the endomorphism algebra. Because it's supposed to be the tangent space at the identity of GLV.
Right. And when you are taking the translation, you are taking the translation on where?
In here.
Right.
So A must be invertible, right? A has that A not equal to 0. Then left translation becomes a diffeomorphism on GLV. But the derivative I can take on the whole vector space. And there it's linear in the whole vector space. Therefore, its derivative is itself. Okay? So I want to take coordinates, I claim the natural coordinates in this vector space. Which are called Yij, which is hence a matrix to its ijth entry. Right, so this would be a natural coordinate for this vector space. Right, and then, of course, ddYij is a basis of the vector space. Because this would be the matrix which has a 1 in the ij spot and everything else 0. Right? So how do I want to compute the Lie bracket? In terms of the definition where I apply to functions, right? If I apply to a function, what is this? This is x applied to y applied to f. That's a function minus y x applied to f. So in terms of derivations, right? It's a lead bracket definition in terms of derivations. So this is f is y is a derivation applied to f. I get a function. X is a derivation applied to this. I get a function. Okay. If I want to compute that, it's sufficient to do this on a basis, to apply to the basis functions. So I want to see what that looks like. So of course this means here I have to take x. So let me now just copying. So I have to understand this function right here. So we understand what the left invariant vector field is. So xa is equal to a times x. X here I should regard as an element of the tangent space identity of GLV, or the n by n matrices. Yeah. And this, of course, was a set of all n by n matrices. So x is the value of the left invariant vector field at the identity, right? And the value at a is on a times x. Okay. So if I take this vector field xa and apply it to the coordinate function, what do I get? Well, how do I define this as a derivation? So by definition of a derivation, this is dyij applied to x sub a at the corresponding point, I guess. This at the point A. But these coordinates yij, they're again linear. Right? So yij is linear. So derivative is itself again. Right? So this would be yij applied to xa. This is a linear map, so derivative itself. And this, of course, is then ax. It's ij's component. Okay. And now do it the other way around. So now we're almost done. Where is it? Here, this is what we want to plug in. Maybe I can do it here already. So so x8 applied to yij is the ij's component, the point A. Of course, I should write this as the vector field x applied to the function which sends A to axij. Right, this here would be the ij's component of A times x. A times, well, sorry, what vector? This is a vector field y, so x. This is a y. That's a linear function again, right? So derivative itself. So I just get that this is equal to because where do I want to differentiate? I think I want to differentiate at the identity. So then this vector would have to be taken at the identity, then applied to these functions. This I have to do out as a function, right? So xe applied to this function. Function is linear, so I just apply a by x. And the derivative of this map is just itself again. I have to do it at the point, at this point here, applied to xe, so it's xy ij. So, well, that's the first part, right? This is this part, of course. Then I'll do it the other way around. Minus, I just switch y and x. So each step is simple linearity. But let me now summarize what we proved. What did we prove? We proved that if I take x, y, add the identity, apply to the function y, the coordinate function yj, I get x, y minus yx, ij entry. Right. X, y, ij minus yx, ij. So that's what I proved so far. Right? So why am I done? Well, what do I have to say? Because these are left invariant vector fields, I only have to compute the Lie bracket at the identity. But that's how I identify my left invariant vector field with a tangent space identity. So that's all I need to know. I apply to the coordinate function, I get this expression. So of course, I guess now I just have to make the remark that, well, if I know a value applied to the coordinate function, sorry, this is equal to the sum apply the coordinate function and then multiply the vector field. This is a general principle for a vector field. When I write a vector field as a sum of the coordinate vector fields, I just take a vector field applied to the functions. And these are just computed. That's what I computed. So here I get summation, the ijth component of xy minus yx. ddyi. Of course, this now means, interpreted, that xy is xy minus yx. So both the left and right are computed in that basis, and the ijth component agrees with each other. Okay. And we do have very nice formulas for the left invariant vector fields, right? So that's what they look like. It's very simple. In general, they're hard to compute. Okay, so that's a basic example of a Lie group in its Lie algebra. And so maybe later on we're going to reduce everything to that, more or less. Okay. Now Lie subgroups. H and G are Lie groups. H is contained in G. Is called a Lie subgroup. If two conditions are satisfied, A is a subgroup algebraically, and B it's an immersed submanifold. So X a 1, 2, 1. Immersed submanifold. So, of course, remember there's usual kind of technical difficulties one has. If it's immersed, it means that the topology on H may not be the submanifold topology. Right? So it's just an immersed submanifold. And the example you should think of that presents difficulties, and that is important if I take my Lie group to be a 2-torus. So in this picture here, and I take H to be R, sitting inside the 2-torus with an irrational slope. So slope is in R minus Q. Then this thing is dense in the torus, right? So now H is dense in S1 cross S1. But certainly it's a subgroup, right? If I add two things in the straight line or stay in the straight line. It's clearly one-to-one, it's immersed, right? So it should be considered as a Lie subgroup of the torus. But of course, the subspace topology is not the topology of the subgroup. Okay, and thus such things have to be allowed. And we're going to see shortly why it's important to allow such things. So they aren't always embedded. Even exercise is that H is embedded in G. If and only if it's closed. So it's precise this issue of is the submanifold closed or not. Okay, that's a Lie subgroup. Then in a similar fashion, I can define a Lie subalgebra. So if V comma bracket is a Lie algebra, then a subspace, so a linear subspace, is a subalgebra if brackets stay in it. And it's a subalgebra of the algebra. So I have subgroups, I have subalgebras, and of course the natural question is now how are they related? If I have a subgroup, what does that mean about the subalgebras? So for that, it's actually best to talk more generally about homomorphisms. If you want to, the subgroup is a special case of homomorphism where the inclusion is a homomorphism. So let's define what I mean by a Lie group homomorphism. So phi from H to G, so H and G are Lie groups. Phi from H to G is a Lie group homomorphism. If, again, the obvious conditions, right, A must be a group homomorphism in the group sense, and phi should be smooth. Then it's a Lie group homomorphism. And when I have such a Lie group homomorphism, I can. So then I have the. Okay, let me write down the proposition. Phi from H to G is a Lie group homomorphism. Then I claim that. So now I can look at the derivative of phi at identity in the ordinary sense, right? This goes from tangent space of E at H into tangent space of phi of E, which is again E of G, because phi is a homomorphism. So this is what I call the Lie algebra of the Lie group H. This is what I call the Lie algebra of Lie group G. So I get a map from H to G. A linear map from H to G, and now the natural claim is that that d phi at E is a Lie algebra homomorphism. And usually we're going to, so I'm going to prove this in a minute. I'm going to drop the name E, right? So if phi is a morphism from H to G, I'm just going to denote by d phi the homomorphism of the D algebras, right? But we're going to see in a minute that this map completely determines phi. Right? So if I know this map, then I know phi in a certain sense. Again, before I come to the proof, a corollary, if H contained in G is a Lie subgroup, then H contained in G is a Lie subalgebra. Right, in the sense of Lie algebras. Right. Of course, this is naturally contained in here because they're the tangent space identity, but it says that the brackets of H are simply the brackets of G restricted to H. Of course, here this follows by just taking phi to be the inclusion. Right, if H is a subgroup, inclusion homomorphism, and then that's exactly what this is. Right, the derivative of inclusion is just the identity. So this just becomes the inclusion of the Lie algebras, and that's a subalgebra. Because that's important, right? If I have a subgroup, I get a subalgebra. Okay, so what needs to be proved is this claim right here. So let's see, what do we need to prove? Yes. For this, one has to remember, again, something about Lie brackets, something a little bit more general than what I used before. So here's the general property of Lie brackets. Let's say I have a map from M to N, which is just C infinity, not a diffeomorphism. And I have two vector fields, X and Y. I'll say X is a vector field on N. Y is a vector field on the range N. Then I'll say X and Y are F related. If the derivative of F at a point P applied to X at P is Y at F of P. Then I call the two vector fields F related. Notice, of course, the image of F in M could be wild in here, right? And assuming nothing about the map F except for C infinity. Because here I'm assuming there's a smooth vector field on N whose restriction to the image is related in this fashion. Okay, if that's the case, I call this smooth vector field M and this smooth vector field N F related. Okay. And then the fact from calculus is that if xi and yi are F related, then the Lie bracket x1, y, x2 is F related to the Lie bracket of y1, y2. So in other words, the equation we've used for diffeomorphism, so df of p applied to the Lie bracket is a Lie bracket which is y1, y2. Right, that's what this says. It says that this Lie bracket is X related to this Lie bracket. What does it mean? The DFP applied to this is this. Right? We've used it for diffeomorphisms, but now it's this is a more subtle statement because F is just smooth. Okay. So I'm going to use this fact about Lie brackets. Has everyone seen that fact? If not, it's an exercise. Where am I? We want to prove this claim here. So maybe I don't need this. So what do we have to prove? Let's write down what we have to prove. So phi goes from H to G. Right? D phi E goes from H to G. So let's take two vectors in H, which I regard as a tangent space at the identity of H. Then I get two corresponding vectors in G, tangent space of G at the identity, and now I can define the corresponding left invariant vector fields. Right, so let xi be left invariant on H such that xi at the identity is vi and yi